The lead-acid battery was invented in 1859 by French physicist Gaston Planté, copyright, and is the oldest type of rechargeable battery. Despite having a very low energy-to-weight ratio and a low energy-to-volume ratio, its ability to supply high surge currents means that the cells have a relatively large power-to-weight ratio. These features, along with their low cost, makes it attractive for use in motor vehicles to provide the high current required by automobile starter motors. As they are inexpensive compared to newer technologies, lead-acid batteries are widely used even when surge current is not important and other designs could provide higher energy densities. Large-format lead-acid designs are widely used for storage in backup power supplies and cell phone towers, high-availability settings like hospitals, and stand-alone power systems. For these roles, modified versions of the standard cell may be used to improve storage times and reduce maintenance requirements. Gel cells and absorbed glass mat batteries are common in these roles, collectively known as Vrla batteries. Lead-acid battery sales account for 45% of the value from batteries sold worldwide, a manufacturing market value of about $15 billion. History. The French scientist Corrosion observed in 1801 that wires that had been used for electrolysis experiments would themselves provide a small amount of secondary current after the main battery had been disconnected. In 1859, Gaston Planté copyright lead-acid battery was the first battery that could be recharged by passing a reverse current through it. Planté copyright's first model consisted of two lead sheets separated by rubber strips and rolled into a spiral. His batteries were first used to power the lights in train carriages while stopped at a station. In 1881, Camille Alphonse Farr invented an improved version that consisted of a lead grid lattice, into which a lead oxide paste was pressed, forming a plate. This design was easier to mass-produce. An early manufacturer of lead-acid batteries was Henri Tudor. In the 1970s, the valve-regulated lead-acid battery was developed. It uses a gel electrolyte instead of a liquid, allowing the battery to be used in different positions without leakage. However, gel electrolyte batteries for any position date from 1930s and even in late 1920s portable suitcase radio sets allowed the cell vertical or horizontal due to valve design. Electrochemistry, discharge. In the discharged state, both the positive and negative plates become lead, sulfate, PbSO4, and the electrolyte loses much of its dissolved sulfuric acid and becomes primarily water. The discharge process is driven by the conduction of electrons from the negative plate back into the cell at the positive plate in the external circuit. Negative plate reaction, PbS, plus SO4, AC, a PbSO4, S, plus H plus, AC, plus 2A, positive plate reaction, PbO2, S, plus SO4, AC, plus 3 hours plus, AC, plus 2A, a PbSO4, S, plus 2 hours, 2O, L. The total reaction can be written as, Pb, S, plus PbO, 2, S, plus 2 hours, 2SO, 4, AC, a 2 PbSO, 4, S, plus 2 hours, 2O, L. The sum of the molecular masses of the reactants is 642.6 grams per mole, so theoretically, a cell can produce 2 faradays of charge from 642.6 G of reactants, or 83.4 ampere-hours per kilogram. For a 2-volt cell, this comes to 167 watt-hours per kilogram of reactants, but a lead-acid cell in practice gives only 40 watt-hours per kilogram of battery, due to the mass of the water and other constituent parts. Charging. In the charged state, each cell contains negative plates of elemental lead and positive plates of lead, oxide, PbO2, in an electrolyte of approximately 33.5% WW sulfuric acid, H2SO4. The charging process is driven by the forcible removal of electrons from the positive plate and the forcible introduction of them to the negative plate by the charging source. Negative plate reaction, PbSO4, S, plus H plus, AC, plus 2A, a Pb, S, plus SO4, AC, positive plate reaction, PbSO4, S, plus 2 hours, 2O, L, a PBO, 2, S, plus SO, 4, AC, plus 3 hours plus, AC, plus 2A. Oval charging with high charging voltages generates oxygen and hydrogen gas by electrolysis of water, which is lost to the cell. Periodic maintenance of lead-acid batteries requires inspection of the electrolyte level and replacement of any water that has been lost. Due to the freezing point depression of the electrolyte, as the battery discharges and the concentration of sulfuric acid decreases, the electrolyte is more likely to freeze during winter weather when discharged. Ion motion: during discharge, H+ produced at the negative plates and from the electrolyte solution moves to the positive plates where it is consumed, while SO4 is consumed at both plates. The reverse occurs during charge. This motion can be by diffusion through the medium or by flow of a liquid electrolyte medium. Since the density is greater when the sulfuric acid concentration is higher, the liquid will tend to circulate by convection. Therefore a liquid medium cell tends to rapidly discharge and rapidly charge more efficiently than an otherwise similar gel cell. Voltages for common usages: these are general voltage ranges per cell. Open circuit at full charge, 2.10 V, open circuit at full discharge, 1.95 V, loaded at full discharge, 1.75 V, continuous preservation charging, 2.23 V for gelled electrolyte, 2.25 V for AGM and 2.32 V for flooded cells. All voltages are at 20 AA degrees Celsius, and must be adjusted by a 0.0235 volts per a degree Celsius for temperature changes. Float voltage recommendations vary among manufacturers. Precise float voltage is critical to longevity. Insufficient voltage is almost as detrimental as excessive voltage. Typical charging: 2.37 a 2.4 V, equalization charging, 2.5 V for no more than 2 hours. Battery temperature must be absolutely monitored. Gassing threshold, 2.4 V, measuring the charge level. Because the electrolyte takes part in the charge-discharge reaction, this battery has one major advantage over other chemistries. It is relatively simple to determine the state of charge by merely measuring the specific gravity of the electrolyte. The SG falls as the battery discharges. Some battery designs include a simple hydrometer using colored floating balls of differing density. When used in diesel-electric submarines, the SG was regularly measured and written on a blackboard in the control room to indicate how much longer the boat could remain submerged. The battery's open circuit voltage can also be used to gauge the state of charge. If the connections to the individual cells are accessible, then the state of charge of each cell can be determined, which can provide a guide as to the state of health of the battery as a whole. Construction: plates. The lead-acid cell can be demonstrated using sheet lead plates for the two electrodes. However, such a construction produces only around 1 ampere for roughly postcard-sized plates, and for only a few minutes. Gaston Planté copyright found a way to provide a much larger effective surface area. In Planté copyright's design, the positive and negative plates were formed of two spirals of lead foil, separated with a sheet of cloth and coiled up. The cells initially had low capacity, so a slow process of forming was required to corrode the lead foils, creating lead dioxide on the plates and roughening them to increase surface area. Initially this process used electricity from primary batteries. When generators became available after 1870, the cost of production of batteries greatly declined. Planté copyright plates are still used in some stationary applications, where the plates are mechanically grooved to increase their surface area. Far-pasted plate construction is typical of automotive batteries. Each plate consists of a rectangular lead grid alloyed with antimony or calcium to improve the mechanical characteristics. The holes of the grid are filled with a paste of red lead and 33% dilute sulfuric acid. The paste is pressed into the holes in the grid, which are slightly tapered on both sides to better retain the paste. This porous paste allows the acid to react with the lead inside of the plate, increasing the surface area many-fold. Once dry, the plates are stacked with suitable separators and inserted in the battery container. An odd number of plates is usually used, with one more negative plate than positive. Each alternate plate is connected. The positive plates are the chocolate brown color of lead dioxide, and the negative are the slate gray of spongy lead at the time of manufacture. In this charged state the plates are called formed. One of the problems with the plates is that the plates increase in size as the active material absorbs sulfate from the acid during discharge, and decrease as they give up the sulfate during charging. This causes the plates to gradually shed the paste. It is important that there is room underneath the plates to catch this shed material. If it reaches the plates, the cell short-circuits. The paste contains carbon black, blank fikes and lignosulfonate. The blank fikes acts as a seed crystal for the lead-to-lead sulfate reaction. The blank fikes must be fully dispersed in the paste in order for it to be effective. The lignosulfonate prevents the negative plate from forming a solid mass during the discharge cycle, instead enabling the formation of long needlier-like crystals. The long crystals have more surface area and are easily converted back to the original state on charging. Carbon black counteracts the effect of inhibiting formation caused by the lignosulfonates. Sulfonated naphthalene condensate dispersant is a more effective expander than lignosulfonate and speeds up formation. This dispersant improves dispersion of barium sulfate in the paste, reduces hydroset time, produces a more breakage-resistant plate, reduces fine lead particles and thereby improves handling and pasting characteristics. It extends battery life by increasing end-of-charge voltage. Sulfonated naphthalene requires about 1/3 to 1/2 the amount of lignosulfonate and is stable to higher temperatures. Practical cells are not made with pure lead but have small amounts of antimony, tin, calcium or selenium alloyed in the plate material to add strength and simplify manufacture. The alloying element has a great effect on the life and water consumption of the batteries. Antimony alloyed plates provide longer life but calcium alloyed plates are much preferred over antimony for their 8 times lower water consumption. Due to the high price of antimony, nearly all car batteries, valve-regulated sealed batteries, and most other non-industrial batteries have been made with lead-calcium grids since the early 1990s and possibly earlier. Tin was added to lead-calcium cells to reduce the corrosion and open circuit effect. Tin helps to reduce this corrosion, but the benefit was deemed not worth $20 per pound, and many manufacturers dropped the tin. It is now rare to find antimony cells, with exception of motive power. It is possible to make lead-antimony positive plates and lead-calcium negatives, however, antimony is plated out onto the negatives and this causes the water-saving benefit of calcium negatives to be lost. While it can be argued that calcium saves water and maintenance costs, it is almost never worth cutting the battery life from 20 years to 5. About 60% of the weight of an automotive-type lead-acid battery rated around 60 Oh is lead or internal parts made of lead. The balance is electrolyte, separators, and the case. Separators between the positive and negative plates prevent short circuit through physical contact, mostly through dendrites, but also through shedding of the active material. Separators obstruct the flow of ions between the plates and increase the internal resistance of the cell. Wood, rubber, glass fiber mat, cellulose, and PVC or polyethylene plastic have been used to make separators. Wood was the original choice, but deteriorated in the acid electrolyte. Rubber separators are stable in battery acid. Rubber provides valuable electrochemical advantages that other materials cannot. An effective separator must possess a number of mechanical properties, such as permeability, porosity, pore size distribution, specific surface area, mechanical design and strength, electrical resistance, ionic conductivity, and chemical compatibility with the electrolyte. In service, the separator must have good resistance to acid and oxidation. The area of the separator must be a little larger than the area of the plates to prevent material shorting between the plates. The separators must remain stable over the battery's operating temperature range. Absorbed glass mat. In the absorbed glass mat design, or AGM for short, the spacer between the cells is replaced by a glass fiber mat soaked in electrolyte. There is only enough electrolyte in the mat to keep it wet, and if the battery is punctured the electrolyte will not flow out of the mats. Likewise, the mat greatly reduces evaporation, to the point that the batteries do not require periodic refilling of the water. This combination of features allows the battery to be completely sealed, which makes them useful in portable devices and similar roles. To address the formation of hydrogen gas during discharge, calcium is added to the plates to absorb the gas. This only works during slow discharges, and gas buildup remains a problem when the battery is deeply or rapidly discharged. To deal with these events, AGMs often include a one-way blow-off valve, and are often known as valve-regulated lead-acid, or VRLA, designs. Another advantage to the AGM design is that the electrolyte becomes the separator material, and mechanically strong. This allows the plate stack to be compressed together in the battery shell, slightly increasing energy density compared to liquid or gel versions. AGM batteries often show a characteristic bulging in their shells when built in common rectangular shapes. The mat also prevents the vertical motion of the electrolyte within the battery. When a normal wet cell is stored in a discharged state, the heavier acid molecules tend to settle to the bottom of the battery, causing the electrolyte to stratify. When the battery is then used, the majority of the current flows only in this area, and the bottom of the plates tend to wear out rapidly. This is one of the reasons a conventional car battery can be ruined by leaving it stored for a long period and then used and recharged. The mat significantly prevents this stratification, eliminating the need to periodically shake the batteries, boil them, or run an equalization charge through them to mix the electrolyte. Stratification also causes the upper layers of the battery to become almost completely water, which can freeze in cold weather. AGMs are significantly less susceptible to damage due to low temperature use. Gelled electrolytes. During the 1970s, researchers developed the sealed version or gel battery, which mixes a silica gelling agent into the electrolyte. This converts the formerly liquid interior of the cells into a semi-stiff paste, providing many of the same advantages of the AGM. Such designs are even less susceptible to evaporation and are often used in situations where little or no periodic maintenance is possible. Gel cells also have lower freezing and higher boiling points than the liquid electrolytes used in conventional wet cells and AGMs, which makes them suitable for use in extreme conditions. The only downside to the gel design is that the gel prevents rapid motion of the ions in the electrolyte, which reduces carrier mobility and thus surge current capability. For this reason, gel cells are most commonly found in energy storage applications like off-grid systems. Maintenance-free, sealed, and VRLA, both gel and AGM designs are sealed, do not require watering, can be used in any orientation, and use a valve for gas blow-off. For this reason, both designs can be called maintenance-free, sealed and VRLA. However, it is quite common to find resources stating that these terms refer to one or another of these designs, specifically. Applications. Most of the world's lead-or-acid batteries are automobile starting, lighting and ignition batteries, with an estimated 320 million units shipped in 1999. In 1992 about 3 million tons of lead were used in the manufacture of batteries. Wet cell standby batteries designed for deep discharge are commonly used in large backup power supplies for telephone and computer centers, grid energy storage, and off-grid household electric power systems. Lead-or-acid batteries are used in emergency lighting and to power some pumps in case of power failure. Traction batteries are used in golf carts and other battery electric vehicles. Large lead-or-acid batteries are also used to power the electric motors in diesel-electric submarines when submerged, and are used as emergency power on nuclear submarines as well. Valve-regulated lead-acid batteries cannot spill their electrolyte. They are used in backup power supplies for alarm and smaller computer systems, and for electric scooters, electric wheelchairs, electrified bicycles, marine applications, battery electric vehicles or micro-hybrid vehicles, and motorcycles. Lead-or-acid batteries were used to supply the filament voltage, with 2V common in early vacuum tube radio receivers. Portable batteries for miners' cap lamps headlamps typically have 2 or 3 cells. Cycles. Starting batteries. Lead-acid batteries designed for starting automotive engines are not designed for deep discharge. They have a large number of thin plates designed for maximum surface area, and therefore maximum current output, but which can easily be damaged by deep discharge. Repeated deep discharges will result in capacity loss and ultimately in premature failure, as the electrodes disintegrate due to mechanical stresses that arise from cycling. Starting batteries kept on continuous float charge will have corrosion in the electrodes which will result in premature failure. Starting batteries should be kept open circuit but charged regularly to prevent sulfation. Starting batteries are lighter weight than deep cycle batteries of the same battery dimensions, because the cell plates do not extend all the way to the bottom of the battery case. This allows loose disintegrated lead to fall off the plates and collect under the cells, to prolong the service life of the battery. If this loose debris rises high enough it can touch the plates and lead to failure of a cell, resulting in loss of battery voltage and capacity. Deep cycle batteries. Specially designed deep cycle cells are much less susceptible to degradation due to cycling, and are required for applications where the batteries are regularly discharged, such as photovoltaic systems, electric vehicles and uninterruptible power supplies. These batteries have thicker plates that can deliver less peak current, but can withstand frequent discharging. Some batteries are designed as a compromise between starter and deep cycle batteries. They are able to be discharged to a greater degree than automotive batteries, but less so than deep cycle batteries. They may be referred to as marine motorhome batteries, or leisure batteries. Fast and slow charge and discharge. The capacity of a lead or acid battery is not a fixed quantity but varies according to how quickly it is discharged. An empirical relationship between discharge rate and capacity is known as Picard's law. When a battery is charged or discharged, only the reacting chemicals, which are at the interface between the electrodes and the electrolyte, are initially affected. With time, the charge stored in the chemicals at the interface, often called interface charge, or surface charge, spreads by diffusion of these chemicals throughout the volume of the active material. Consider a battery that has been completely discharged. If it then is given a fast charge for only a few minutes, the battery plates charge only near the interface between the plates and the electrolyte. In this case the battery voltage might rise to a value near that of the charger voltage. This causes the charging current to decrease significantly. After a few hours this interface charge will spread to the volume of the electrode and electrolyte. This leads to an interface charge so low that it may be insufficient to start the car. As long as the charging voltage stays below the gassing voltage, battery damage is unlikely, and in time the battery should return to a nominally charged state. Valve-regulated. In a valve-regulated lead-acid battery the hydrogen and oxygen produced in the cells largely recombine into water. Leakage is minimal, although some electrolyte still escapes if the recombination cannot keep up with gas evolution. Since VRLA batteries do not require regular checking of the electrolyte level, they have been called maintenance-free batteries. However, this is somewhat of a misnomer. VRLA cells do require maintenance. As electrolyte is lost, VRLA cells dry out, and lose capacity. This can be detected by taking regular internal resistance, conductance or impedance measurements. Regular testing reveals whether more involved testing and maintenance is required. Recent maintenance procedures have been developed allowing rehydration, often restoring significant amounts of lost capacity. VRLA types became popular on motorcycles around 1983, because the acid electrolyte is absorbed into the separator, so it cannot spill. The separator also helps them better withstand vibration. They are also popular in stationary applications such as telecommunications sites, due to their small footprint and installation flexibility. The electrical characteristics of VRLA batteries differ somewhat from wet cell lead or acid batteries, requiring caution in charging and discharging. Sulfation and desulfation. Lead or acid batteries lose the ability to accept a charge when discharged for too long due to sulfation, the crystallization of lead sulfate. They generate electricity through a double sulfate chemical reaction. Lead and lead dioxide, The active materials on the battery's plates react with sulfuric acid in the electrolyte to form lead sulfate. The lead sulfate first forms in a finely divided, amorphous state, and easily reverts to lead dioxide and sulfuric acid when the battery recharges. As batteries cycle through numerous discharges and charges, some lead sulfate is not recombined into electrolyte and slowly converts to a stable crystalline form that no longer dissolves on recharging. Thus, not all the lead is returned to the battery plates, and the amount of usable active material necessary for electricity generation declines over time. Sulfation occurs in lead or acid batteries when they are subjected to insufficient charging during normal operation. It impedes recharging. Sulfate deposits ultimately expand, cracking the plates and destroying the battery. Eventually so much of the battery plate area is unable to supply current that the battery capacity is greatly reduced. In addition, the sulfate portion is not returned to the electrolyte as sulfuric acid. It is believed that large crystals physically block the electrolyte from entering the pores of the plates. Sulfation can be avoided if the battery is fully recharged immediately after a discharge cycle. A white coating on the plates may be visible. Batteries that are sulfated show a high internal resistance and can deliver only a small fraction of normal discharge current. Sulfation also affects the charging cycle, resulting in longer charging times, less efficient and incomplete charging, and higher battery temperatures. Desulfation is the process of reversing the sulfation of a lead-acid battery. It is believed that desulfation can be achieved by high current pulses produced between the terminals of the battery. It is believed that this technique, also called pulse conditioning, breaks down the sulfate crystals that are formed on the battery plates. Pulses must last longer than the resonant frequency of the battery. Short pulses simply feed energy wastefully into the resistive components of this resonant circuit and virtually none into the battery. Electronic circuits are used to regulate the pulses of different widths and frequency of high current pulses. These can also be used to automate the process since it takes a long period of time to desulfate a battery fully. Battery chargers designed for desulfating lead-acid batteries are commercially available. A battery will be unrecoverable if the active material has been lost from the plates, or if the plates are bent due to over-temperature or overcharging. Batteries which have sat unused for long periods of time can be prime candidates for desulfation. A long period of self-discharge allows the sulfate crystals to form and become very large. Some typical cases where lead-acid batteries are not used frequently enough are planes, boats, old cars, and home power systems with battery banks that are underutilized. Some charging techniques can aid in prevention such as equalization charging and cycles through discharging and charging regularly. It is recommended to follow battery manufacturer instructions for proper charging. SLI batteries suffer most deterioration because vehicles normally stand unused for relatively long periods of time. Deep cycle and motive power batteries are subjected to regular controlled overcharging, hence eventually succumb to corrosion of the positive plate grids, not to sulfation. Stratification: a typical lead or acid battery contains a mixture with varying concentrations of water and acid. Sulfuric acid has a higher density than water, which causes the acid formed at the plates during charging to flow downward and collect at the bottom of the battery. Eventually the mixture will again reach uniform composition by diffusion, but this is a very slow process. Repeated cycles of partial charging and discharging will increase stratification of the electrolyte, reducing the capacity and performance of the battery because the lack of acid on top limits plate activation. The stratification also promotes corrosion on the upper half of the plates and sulfonation at the bottom. Periodic overcharging creates gaseous reaction products at the plate, causing convection currents which mix the electrolyte and resolve the stratification. Mechanical stirring of the electrolyte would have the same effect. Batteries in moving vehicles are also subject to sloshing and splashing in the cells, as the vehicle accelerates, brakes, and turns. Risk of explosion. Excessive charging electrolyzes some of the water, emitting hydrogen and oxygen. This process is known as gassing. Wet cells have open vents to release any gas produced, and VRLA batteries rely on valves fitted to each cell. Wet cells come with catalytic caps to recombine any emitted hydrogen. A VRLA cell normally recombines any hydrogen and oxygen produced inside the cell, but malfunction or overheating may cause gas to build up. If this happens, the valve vents the gas and normalizes the pressure, producing a characteristic acid smell. Valves can sometimes fail, however, if dirt and debris accumulate, allowing pressure to build up. If the accumulated hydrogen and oxygen within either a VRLA or wet cell is ignited, an explosion results. The force can burst the plastic casing or blow the top off the battery, spraying acid and casing fragments. An explosion in one cell may ignite the combustible gas mixture in remaining cells. In a poorly ventilated area, connecting or disconnecting a closed circuit directly to the battery terminals may cause an explosion as the sparks produced ignite the gas mixtures vented from the cells. The cell walls of VRLA batteries typically swell when the internal pressure rises. The deformation varies from cell to cell, and is greater at the ends where the walls are unsupported by other cells. Such overpressurized batteries should be carefully isolated and discarded. Personnel working near batteries at risk for explosion should protect their eyes and exposed skin from burns due to spraying acid and fire by wearing a face shield, overalls, and gloves. Using goggles instead of a face shield sacrifices safety by leaving one's face exposed to acid and heat from a potential explosion. Environmental concerns. According to a 2003 report entitled Getting the Lead Out, by Environmental Defense and the Ecology Center of Ann Arbor, Michigan, the batteries of vehicles on the road contained an estimated 2,600,000 metric tons of lead. Some lead compounds are extremely toxic. Long-term exposure to even tiny amounts of these compounds can cause brain and kidney damage, hearing impairment, and learning problems in children. The auto industry uses over 1 million metric tons every year, with 90% going to conventional lead-acid vehicle batteries. While lead recycling is a well-established industry, more than 40,000 metric tons ends up in landfills every year. According to the Federal Toxic Release Inventory, another 70,000 metric tons are released in the lead mining and manufacturing process. Attempts are being made to develop alternatives because of concerns about the environmental consequences of improper disposal and of lead smelting operations, among other reasons. Alternatives are unlikely to displace them for applications such as engine starting or backup power systems, since the batteries are low cost although heavy. Recycling. Lead or Euro-acid battery recycling is one of the most successful recycling programs in the world. In the United States, 97% of all battery lead was recycled between 1997 and 2001. An effective pollution control system is a necessity to prevent lead emission. Continuous improvement in battery recycling plants and furnace designs is required to keep pace with emission standards for lead smelters. Additives. Chemical additives have been used ever since the lead-acid battery became a commercial item, to reduce lead sulfate buildup on plates and improve battery condition when added to the electrolyte of a vented lead or Euro-acid battery. Such treatments are rarely, if ever, effective. Two compounds used for such purposes are Epsom salts and EDTA. Epsom salts reduces the internal resistance in a weak or damaged battery and may allow a small amount of extended life. EDTA can be used to dissolve the sulfate deposits of heavily discharged plates. However, the dissolved material is then no longer available to participate in the normal charge-discharge cycle, so a battery temporarily revived with EDTA will have a reduced life expectancy. Residual EDTA in the lead or Euro-acid cell forms organic acids which will accelerate corrosion of the lead plates and internal connectors. The active materials change physical form during charge-discharge, resulting in growth and distortion of the electrodes, and shedding of electrode into the electrolyte. Once the active material has fallen out of the plates, it cannot be restored into position by any chemical treatment. Similarly, internal physical problems such as cracked plates, corroded connectors, or damaged separators cannot be restored chemically. Corrosion problems. Corrosion of the external metal parts of the lead or Euro-acid battery results from a chemical reaction of the battery terminals, lugs and connectors. Corrosion on the positive terminal is caused by electrolysis, due to a mismatch of metal alloys used in the manufacture of the battery terminal and cable connector. White corrosion is usually lead or zinc sulfate crystals. Aluminum connectors corrode to aluminum sulfate. Copper connectors produce blue and white corrosion crystals. Corrosion of a battery's terminals can be reduced by coating the terminals with petroleum jelly or a commercially available product made for the purpose. If the battery is overfilled with water and electrolyte, thermal expansion can force some of the liquid out of the battery vents onto the top of the battery. This solution can then react with the lead and other metals in the battery connector and cause corrosion. The electrolyte can weep from the plastic to lead seal where the battery terminals penetrate the plastic case. Acid fumes that vaporize through the vent caps, often caused by overcharging, and insufficient battery box ventilation can allow the sulfuric acid fumes to build up and react with the exposed metals. Maintenance precautions: ammonia can neutralize spilled battery acid. Surplus ammonia and water evaporate, leaving an ammonium sulfate residue. Sodium bicarbonate is also commonly used for this purpose. Sizing nomenclature: with a broad range of possible electrical attributes, a part number nomenclature is used by many battery manufacturers to convey basic information such as voltage, ampere-hour capacity, and terminals. The format follows a pattern such as MFG voltage capacity. Some vendors append a suffix, indicating the terminal types, terminal locations, and battery dimensions. Batteries for passenger motor vehicles usually use BCI sizing nomenclature. See also: automotive battery, battery room, dry cell, rechargeable battery, wet cell, history of the battery, references. Lead-acid battery desulfator: 1. Battery plate sulfation, 2. Battery desulfation, 3. Lead-acid batteries, 4. DC supply. 5. Some technical details on lead-acid batteries. 6. External links: Battery Council International, Lead-Acid Battery Manufacturers Trade Organization. Car and Deep Cycle Battery Frequently Asked Questions, TOX Facts, Lead, National Pollutant Inventory Lead and Lead Compounds Fact Sheet, Case Studies in Environmental Medicine Lead Toxicity, Lead-Acid Battery Desulfator, Battery Plate Sulfation, Battery Desulfation, Technical Details on Lead-Acid Batteries, Primer on Lead-Acid Storage Batteries at the U.S. Department of Energy. Battery Discharges, Description and Treatment of Sulfated Batteries.